Okay, so welcome to the second part of my talk. In this part, we'll try to give a sketch. I'll try to give a sketch of the proof of the main theorem. Last time, what I did was talking about the relation with normal subgroup theorem, but for the purpose of this next part, this was the most important part. So we translated the statement about infinite injectivity radius into something about the orbit closures in the space sub G, which was the space of subgroups, closed subgroups of G. So we'll use that to translate our theorem into the language of closed subgroups of G. So let me state it as theorem A prime. There will be even A prime prime later. So theorem A prime would say the following. So if so G in this part of talk, G will be always a simple higher rank. So I'll put this assumption here and not mention it anymore. So if theorem A prime would say that if lambda is in sub G is discrete, so it's important to assume that because not all closed subgroups of G are discrete. And the covolume is infinite, so volume of G mod gamma is infinite, then the orbit closure of gamma contains the trivial subgroup. So yeah, to be perfectly precise, it can also contain the center or something like this. So let me add another assumption, higher rank, center free. So you can always quotient out by the center. This won't change anything. So from the point of view of local symmetric spaces, this center of G is always in the kernel of the action on X, so it doesn't matter. We can assume that G is center free. So the conclusion will be that closure of lambda in sub G contains the trivial subgroup. Okay, so this is the same thing as theorem A, but what we'll actually prove will be stronger than this. So we not only prove that this orbit closure contains identity, we'll actually show that if you pick a nice symmetric generating measure on G and perform a random walk on sub G, starting from lambda, you will almost surely converge to the trivial subgroup. So this is much stronger. So theorem A prime will be like this. So let mu be a smooth probability measure on G. So smooth means that it's absolutely continuous with respect to R, and that automatically forces its support to generate everything. So it'll be a smooth probability measure on G. Let's assume it's symmetric. Then the following is true. Then we have the following convergence. So limit as n goes to infinity, 1 over n, sum from k equal 0 to n minus 1, Dirac delta at the point lambda, convolution with mu power k. This should converge weakly to the Dirac mass in the trivial group. So this convergence is weak star. And this translates to the statement I said. So if you start from lambda and perform a random walk, you will typically converge to the trivial subgroup. And assumptions for lambda are the same as in the previous point. So this holds for every lambda in sub G, which is discrete, and has infinite covolume. Okay, so from now on, this is what we want to try to prove. And the proof of this theorem will contain inside will be a conclusion of consequence of two other results, which I think are of independent interest. So let me state them. So first will be theorem B, which is kind of a statement that when you start a random walk from lambda in sub G, then you will never venture into the, well, you won't converge to something which is non-discrete. In other words, most of the time you'll see discrete groups, and moreover, there will be kind of uniform discrete. So you won't see subgroups which have too many points in small ball. So to properly state this, let me introduce a new piece of notation. So let's say that sub G D is the set of subgroups in sub G, which are in addition discrete. So theorem B says that if lambda is discrete, so maybe I can now write if lambda is in sub G D and nu is any weak star limit of the sequence defined as above. So let me just copy this. So any weak star limit of this sequence, and now I'm not assuming that this guy is finite covolume, so this doesn't have to be the Dirac delta identity. We just take any limit of the sequence. I claim that it is supported on sub G D. Right, so we remain random walks like to remain inside the set of discrete subgroups. So this has a nice geometric counterpart. So if you translate it back to local symmetric spaces, this statement would say that if you have an infinite volume local symmetric space and you start a random walk on this space, you will typically stay away from very thin parts, because the only way in which you can destroy discreteness is when you start to venture into parts of the space where injectivity radius is smaller and smaller. Okay, and this at this point of view is actually not bad, because that's how we prove it. So idea of the proof of this theorem. If you know, there is a proof of Eskin-Margulis for finite volume locally symmetric spaces of the fact that random walk on such a space doesn't spend much time in a thin part. So our proof of this theorem B is modeled after original proof of Eskin-Margulis. So let's say inspired Eskin-Margulis. In particular, it uses something we now call Margulis functions. So let me state it for locally symmetric spaces, and then you can translate it back to sub G. So if we have a locally symmetric space like this, so let's say we start with this, a function f that goes from this space, so f goes from this space to a set of non-negative real numbers, is called a Margulis function. if the following conditions are satisfied. So first condition, it basically says that f of a point P converges to infinity if and only if injectivity radius at P goes to 0. So f can get large only in the parts of the space where the injectivity radius is very small. And the second condition, just a little bit more technical, is that this function is kind of subharmonic. So what I mean by that is if I look at f of gp d mu g, so where mu is this measure that we started with, some kind of symmetric smooth measure on g, then this average is bounded by some constant c times the value at the center plus a constant b, and this constant c is supposed to be smaller than 1, which is important in this definition. B is any constant. Right, so this, if we didn't have this b, this would be kind of subharmonic function, because whenever you take averages, it gets smaller. Okay, so once you have such a function, so if we have such a function, I claim that this implies that random walk cannot spend too much time in a thin part. So let me write it, random walk, so that, how to state it properly? Well, maybe let me write that these properties imply the following. So they imply that for every natural n, this and basically any p starting point in local symmetric space, when I look at average of this function f with respect to some high convolution of mu, this will remain bounded by some constant m, and m is independent of n, and this inequality, so this plus property 1, which says that f is large if and only if injectivity radius at P is 0, this property implies that random walk doesn't spend much time in the thin part. Again, how to prove it using this function is some pure analysis 1, so I won't bore you with the details. The hard part here is finding this Margulis function. But fortunately for us, such a function was constructed in a recent preprint of Margulis, Sahik, and Ari Levitt. So such function was constructed for any locally symmetric space by Margulis, Gelander. Okay, I should keep the right order. Gelander, Margulis, and Ari Levitt, 2021. Okay, so well, this is something about locally symmetric spaces, but when you use this equivalence between injectivity radius and discreteness, we can translate it back into this statement. So this implies theorem B. Theorem B is proven using Margulis functions. That's the main takeaway. Okay, but now there is a second ingredient in the proof of theorem A prime, which is theorem C, arguably more interesting. So, and theorem C is basically a classification of ergodic stationary measures on the space sub G. So this is classification of ergodic stationary measures on sub G. Sub GD, yeah, discrete subgroups. So on sub G you will have more than on sub GD. So this theorem says the following. So let nu be a probability measure. So let me just say it, be an ergodic mu stationary probability measure on sub GD. And then we'll have the following possibilities. So first possibility is that nu is actually Dirac delta at the trivial subgroup. And the second possibility is that nu is it comes from a lattice. So nu is of the form 1 over volume G mod gamma integral over G mod gamma of Dirac delta gamma conjugate by G dG for some lattice gamma in G. So you'll note that this is very similar to the classification of, if you know, of invariant random subgroups from the Seven Samurai paper, or if you will, from Stuck-Zimmer, because basically there is a theorem of Stuck-Zimmer which basically says that IRSs in higher rank, simple hierarchy groups are of this form. Well, you also have one non-discrete IRS, which is whole group G itself, but after restricting discrete ones, this is all. So it's a bit surprising that you get the same classification if you assume only stationarity. In particular, the corollary of theorem C is that stationary implies invariant, because all those two examples that are allowed are invariant, not just stationary. Right? It's funny. For Stahik, we thought for a moment that this corollary might be true even in rank 1, but then we found counterexamples. So this is really a high rank phenomenon, where you from stationarity you get invariance for free. Right. So now proof of this theorem C is nice. It uses a very beautiful structure result of Neville-Zimmer from 2002. So to prove theorem C, the main ingredient, as the main ingredient, you use the following. So this is a theorem by Neville-Zimmer. I think it's from Annals. And it says it's complete, it's very abstract, very general. So let X nu, or maybe let me use another letter because X is used for symmetric space. So let Y nu be a be an ergodic stationary. So mu stationary, mu is always the same measure, G system. So this is like an ergodic probability measure preserving system, but it's not, the measure is not assumed to be invariant, it's only assumed to be stationary under mu. So I should mention probability. Okay. Then Neveu-Zimmer theorem says that one of the following things must hold. So then either one, mu is G invariant, or two, there exists a factor map, so G equivariant factor map. So relative, so this is also measure preserving. So G equivariant measure preserving factor map from my space Y nu to a quotient G mod Q, nu Q, where Q is a proper parabolic subgroup. And nu Q is the unique mu stationary measure. On this quotient. So it's I think classical result that if your measure mu is smooth, then there is only one such measure. Okay, so right, this is nice theorem. It's kind of, you can think of it as an extension of the intermediate factor theorem. And now how do we use it? Because well, it's not just that theorem C follows directly from this theorem, but I won't have time to give you all the details. So let me just give you one non-trivial consequence of this theorem in the study of stationary measures on sub G, which already should be something surprising, and basically our proof is pushing this idea to the limit. So suppose now that mu is a stationary ergodic measure on, so probability measure on probability measure on sub G. And we have two options. So case one, mu is invariant. Then I'll just tell you that theorem C follows from Stuck-Zimmer. Basically, in this case, nu is an IRS, and IRS is in hierarchical classified. So this follows from classification of IRS. And case two, we have this factor map promised by Neveu-Zimmer's theorem. So there is some factor map to GQ, nu Q. Okay. And what can we get from the existence of this factor map? So because this map is G equivariant, what we'll be able to deduce is that for almost every point, so from almost every point gamma in, so I should write for nu almost every point. For nu almost every lambda in sub G, the stabilizer of this point above under the action of G must be contained in the stabilizer of the image, simply because of G equivariance. So let's maybe call this map, I know, rho. Stabilizer under G action of lambda must be contained in the stabilizer under G action of rho of lambda, right? But this thing is, well, this is certainly some subgroup containing lambda, right? Because well, when you act with elements of lambda itself, it stays the same because it's subgroup. On the other hand, here, because this space is a G mod Q, this thing must be a parabolic subgroup. So this is a conjugate of Q. So those observations alone imply that almost every subgroup lambda in sub GD is contained in some parabolic. And this is our point of starting point. In the proof, we upgrade the statement in some consecutive steps. So for example, we show that you can decompose the measure nu into P invariant measures, or P's are Borel subgroups, minimal parabolics. And those P invariant measures are supported on subgroups containing bigger parabolics. And because the parabolics, they kind of are not really compatible with discrete subgroups, we managed to show that well, this whole setup forces, so there's some work, but this whole setup forces nu to be a Dirac delta identity because, well, maybe let me write, because parabolics are incompatible with stationary discrete subgroups. Well, and that would be a very rough sketch of our proof. So I think that our paper is not so badly written. It's actually, I think it's well written, thanks to Sahik mostly. And if you want to read just a proof for the simple groups, it's not long. So I think with this outline you could, and the paper itself, you could get understood all the details easily. Right, so yeah, that's it. I have to finish. This feels like a lecture, and you can see me in office hours on 22nd of June. Bye.